I'm happy to be invited to participate in this program again this morning here, or morning my time. And I'm going to shift gears a little bit, continue talking about challenges in neuroergonomics, but now kind of more specifically applied to monitoring driver attention systems and semi-automated vehicles. So to give a little bit of a roadmap of what I'll be talking about, I'll talk a little bit about the space and the need for this kind of work. And so levels of driver automation and people's lack of understanding of that, hence the need to monitor whether they're paying attention. They may not even know whether they need to be paying attention. But somehow I think it would be very important if we were able to tell when they're attentive and when they're not. And then a major challenge, bridging the gap from applied research, from laboratory studies to driving simulations to on-road studies at various different levels. And then get back to I still think that we have theoretical challenges that we need to overcome, we need to address. And I think we're kind of maybe just at the tip of the iceberg of some of that. And humans are messy. We do all kinds of things. There's individual differences. We're intra-individual differences and inter-individual differences. And we're not always doing what researchers are hoping we're doing when we're participating in studies and things like that, and we're all over the place. So I think that continues to be a major challenge. And not to mention, I guess, some of the extremely basic things we have just went through, and we're not completely out of a pandemic. And when it comes to challenges for neuroergonomic research, I know a personal challenge for mine, I switched labs shortly before, switched universities from George Mason to Wichita State, shortly before the pandemic broke out. And I have essentially went through a little over a year where I was not allowed to put electrodes and sensors and things on people. So I think, maybe that goes without saying, but this is not just some survey you can send out to people kind of a thing. It's much more challenging work. But to start out, so talking about the problem space, as I'm sure we're all aware, semi-autonomous driving systems are increasingly pervasive, but they're still misunderstood. So for example, in a real recent study that came out, looking at just adaptive cruise control, so that's like if you only had the level 1 driving, which is coming up on the next slide, it's not the regular cruise control. It will literally keep you from running into a car right in front of you. It'll adjust your speed to that car. And people understand it better than they did 10 years ago, but even owners with vehicles equipped with this adaptive cruise control are still not aware of many of the important limitations. And there's been some earlier work that has been real fascinating to suggest even if people are initially aware of some of the limitations of it, they can quickly forget and get into this sense of automation complacency if they don't experience that limitation for a period of time. And I have kind of an anecdotal story about that myself. But I want to talk about these levels of automation before I give that little anecdotal story. So this is the Society of Automotive Engineers, levels of driving automation. I'm going to guess most of us have seen this before. When I talk about semi-automated levels, I'm really talking about level 2 and level 3. Level 2, partial automation. You have lateral and longitudinal lane control. So basically the car can do those basic control tasks of maintaining your speed and your lane position, but the driver's supposed to be paying attention at all times, doing all tactical, strategical maneuvers, monitoring for hazards to the same extent as if they were manually driving. And I'm pretty sure drivers don't even understand this. And even if they do understand this, they're probably not capable of doing that. Level 3 is a slightly higher level. You don't necessarily need to be doing hazard monitoring at all times, but you need to be in a state to resume control within seconds if the system gets outside of its operating parameters. So that's basically what I'm talking about when I just kind of lump these two into semi-automated driving. And I think it's worth pointing out and reminding ourselves that we've studied driving behavior for quite some time now, and at least one, I think, useful way of looking at dividing the driving task into several different levels goes back to Michon's 1985 thing, where the control is that basic level of lateral and longitudinal control, the kinds of things that an experienced driver can basically do almost automatically. That's what is currently being automated. So level 2 automation, which is currently out on the market, the Tesla Autopilot, the GM Super Cruise, those are only level 2 automation, and all they can do are the things that humans already could almost do automatically anyway. Okay, but now when drivers are engaged in that, we're taking that out, but we're expecting them to continue to do all the more challenging tasks. And this taxonomy has been recently supported in on-road studies with on-road naturalistic studies. So going back a bit, earlier, and I'm going to guess most people have heard of this, the first fatal Tesla crash, there were at least 3 bad assumptions according to the National Transportation Safety Board. One was on the part of the automation, and the automation made the assumption that the tractor trailer that was actually cutting in front of the Tesla vehicle was actually part of the sky. It was white, it was a cloudy day. The automation did not detect that that wasn't just part of the sky. That's obviously not good, but further, the other factors or bad assumptions that NTSB declared were, one, that the driver understood the limits of the automation, that the driver would even understand that there was a possibility that the car might confuse that. And the third big one was that the driver was paying attention. Okay, and paying attention, I'm going to say, is one of our big challenges in these. So in these semi-automated vehicles, particularly level 1 and level 2, to a large extent also in level 3, drivers are expected to stay in the loop. They're expected to be paying attention. But A, do they even understand this? And a lot of our recent work has suggested no, they do not. Our work and other people's work, they don't even understand that. But even if they do understand it, it requires vigilance. And that's something humans are just not good at. Maintaining focused attention on something for a long period of time, even if it's critical, humans are not good at that. We shift in and out of different internal, external attentional states, focus, default mode network. We shift in and out of this, particularly when there's very little to do and you're just kind of monitoring something, but you're not having to be an active participant. So what can we do about this? That's the problem space. What can we do about this? I'm suggesting that neuroergonomic methods of monitoring attentional state are one very good possibility to address this issue. So how can we tell if drivers are paying attention when they're not actually driving? Well, a challenge in this, and I'm kind of leaping ahead, I hope to come back to that a little bit, leaping ahead, is this idea of, as Klaus already mentioned, we need to bridge basic research to translational research. There have been a lot of laboratory studies of attention and vigilance, and usually very simple studies, but to what extent can we take any or much of that research and translate it, A, to driving at all, and then driving behavior at the highest level. So in this driving studies of attention and vigilance, there have been some studies on attention and vigilance in simulator studies. Most of my work, honestly, has been in simulators, almost all of it. Um, and I've used a variety of low and high fidelity simulators, but it's all been driving simulators. As was previously mentioned, this has some benefits. We can have carefully controlled studies. We can make sure unexpected things are a lot less likely to happen, but it's not real world driving. You can ramp that up to on-road test tracks. That gives that, now you're in an actual vehicle on a road, um, but you're still not on an open road. There have been a few very limited number of studies on this issue, on-road studies on the open road, but with constraints. We're giving you an artificial task to do. We're not letting you do just whatever you want to do. Going down to the naturalistic study, we do all kinds of things in our car. We all know that. We eat, we drink, we listen to music, we check our, no, we don't do that. We do. We check our phones, we do all these kinds of things. We interact with people. We have conversations with people both in the vehicle, outside the vehicle. More naturalistic settings, we're doing all kinds of different things. Those mess up our studies. That's a real challenge to this area. So just to really take it back to a real basic level, laboratory studies of vigilance are numerous, and generally people have one very discrete stimuli. Lots of distractor stimuli is coming, but rarely they'll get some critical signal that they're supposed to respond to as quickly as possible. Only one signal. And what we typically get from these laboratory studies is the longer you're engaged in that task, the less likely you are to detect that critical signal. So detection rate goes down. And then very often, even if you do detect that signal, you take longer to respond to it. So your response or reaction time goes up. Typical laboratory vigilance results. What is the signal in naturalistic driving? There may be many potential hazards or critical signals. There may be many simultaneous hazards. So what then is the signal, and how can we determine whether or not a driver is aware of it, particularly if they don't need to respond? If the automation maybe has some of that, but we need to make sure that they need to be monitoring the automation as well as the hazards. How do we even know if they're not responding, whether or not they're still attentive to these potential hazards? I think that's where neuroergonomics can really shed light. We can get some index of what's going on with the driver, even if they're not physically responding to something. They're sitting there monitoring a screen. Okay, but so then, as I've already kind of mentioned, driving simulator work, these are just some of the simulators I've used over the years. The top left one is like a basic desktop simulator. You see lots of studies using that. Used at George Mason, a motion-based simulator, higher fidelity. You kind of feel bumps when you go over it. Still not a real car. Currently at Wichita State, I actually have a real car, but it's obviously not going anywhere. There's screens there in front, so it's stationary, but it is a real car. There's lots of different levels of the simulator fidelity. In our lab, we've also used a variety of physiological measures. My kind of go-to tends to be EEG and ERP. So we've quite often looked at parietal alpha and frontal theta for indexes of workload and attention. We've used some other bandwidths and metrics as well, but those are kind of the go-to ones. P300 ERP for assessing workload. And then occasionally, not all the time, but occasionally in combination with heart rate variability, some eye tracking, pupil diameter, things like that. each one of these, and I think this is a challenge that it might be slightly out of line here, but each of these measures, these aren't necessarily even the best measures. These are my go-to measures, and these are a lot of work. And these are a lot of work to train new researchers and students in them. And every time you pick up a new metric, you have to learn that new metric. And that's a big challenge too. There's a lot that goes on behind, conducting these studies. So just quickly to talk about a few of the neuroergonomic approaches we've used in my lab, trying to just kind of keep track of my time here. We've looked at a lot of different things. Mental workload is kind of a go-to, and attentional engagement. We've looked at mind wandering, so trying to detect physiologically whether or not, just whether your mind's on the road. Just because your eyes are on the road doesn't mean your mind is on the road. We've looked at trying to predict ahead of time when people might fail to detect some kind of an automation signal. And then we've scratched the surface at novel attention management approaches. So I'll quickly talk about a couple of these. The mind wandering series has been one of my favorite. It was a lot of fun to do, a lot of work, but a lot of but so even during manual driving, the research suggests that about half the time we're not really paying attention. Our eyes may be on the road, but our mind is not. So we conducted some research to see, hey, could we even detect these periods of time? Could we distinguish between them? Ran a series of different studies in both low fidelity simulators and high fidelity simulators, single day studies, multiple day studies using a variety of different parameters. I won't have time to go into all that, but basically we did have some success. So we found that we could reliably detect when people were mind wandering. They had an increased parietal alpha power and a decreased P300 response to external auditory probes. We had some luck with the heart rate measures. Interbeat interval in particular tended to be longer when a person was mind wandering, and not maybe surprisingly, gaze concentration. So people aren't scanning the roadway, they're looking straight ahead, so their gaze is concentrated. All of these seem to be reliable indicators of mind wandering state. But this was actually during manual driving. So then we began to look at, well, could we do this using partial automation? Could we predict when somebody might? So if we can detect when they're mind wandering, can we do that ahead of time and predict that they're likely to miss some critical signal? We went back to a desktop simulator, really low fidelity simulator with a basic automated lane changing task. And people would see these little arrows suggesting that they needed to change lanes, but they're just monitoring the automation. So they're not, this would be level 2. They're not having to control their speed, and they're not having to control their lane position. They're just monitoring the situation. If that arrow became more red, then they were supposed to indicate that they noticed that. And we were looking at, could we predict whether or not they would notice that signal before they actually got it? Could we predict that they might miss that critical signal? So we had them go through a number of different drives on this, and had some success at this. We again, pre-stimulus alpha or alpha power, parietal alpha power in particular, did provide us a reliable indicator of whether or not people were likely to miss that upcoming signal, suggesting that perhaps something could be done ahead of time if we know the driver's out of the loop and not paying attention. Heart rate variability had a little bit of predictive power, and so did gaze concentration, but neither one were sufficient on their own. So maybe in the near future, at least in simulated driving, we might have some luck at being able to predict when they're out of the loop and need to maybe possibly be brought back in. But does any of that translate to real world driving? Almost all of these, we're giving them an artificial task to do. They're having this oddball paradigm or some other kind of a cue thing. Does that translate to any kind of actual driving? And in the real world. And I think there's a number of challenges which I'll kind of continue, but we need more effective mental models of driving automation, and we need more robust theoretically based metrics. We've also looked at then this notion of, I'm going to kind of skim through this kind of quickly for the sake of time, but could we predict people learning these systems and the rate at which they learn them, and distinguish between novice users of the system and then people that had a little more experience, again with adaptive cruise control and active lane keeping, gave an artificial task, an auditory oddball task, and had some success with this. So when people were engaged with just active cruise control compared to a baseline, we saw a decrease in the P300 response. Interestingly, when they were engaged with two systems, both active cruise control and active lane keeping, we saw even a further reduction in the P300 response, suggesting that more automation was not necessarily easier. They were actually needing to pay even more attention. But again, does any of this translate to more naturalistic conditions? There aren't a lot of studies on road, and certainly not naturalistic conditions yet, that have used neuroergonomics methods. There are a few. I just briefly chose to highlight a couple. One controlled on-road study used EEG and heart rate variability and things like that. A recent paper by Strayer and colleagues that actually found no difference in arousal or cognitive demands based on EEG metrics or ECG metrics between manual driving and partially automated driving. But some of the challenges, and this is certainly not to criticize their work, it's some really important work, but participants were always told when to engage in the automation to a very positive thing. They had two age groups. They drove on different roadways, but they performed an artificial task in addition to the naturalistic driving. They had constraints. They weren't allowed to do other things other than the experimental task. And whenever there was any kind of a hazardous situation, they had to stop the data collection so that it didn't mess up they didn't get too many artifacts in the EEG. Some more promising stuff by one of our own, Klaus Grauman and his colleagues. They've done some studies with promising results saying EEG is a possibility. This wasn't actually on the road, and a couple of caveats about that, though. It's promising, but they did note that any movements related to actual driving produced artifacts in the data, and that the EEG cap itself became uncomfortable over time. So we've got a number of challenges. Increased driving automation doesn't always make things easier, and particularly if people are inexperienced. But these challenges, we still need better sensors. We need better brain imaging techniques. We need new methods to translate this lab sim research to naturalistic setting. And we still need theoretical advances. Just to kind of wrap this up, humans are really messy. As I mentioned, they have inter and intra-individual differences. Many factors that we're often not taking into account can affect the data and the people's response, their knowledge and understanding of the system, emotion, their emotional state at the time, and their fatigue state, social interactions or lack thereof can change physiology. And then all of the other tasks we might do, listening to music, all of these things that we do in naturalistic settings can impact the data. This is a really messy slide of just some of the things that we have thought about in some of our current ongoing work, where we're trying to look at using neuroergonomics measures of identifying loss of vigilance. There's many different ways that loss of vigilance could come from. It could come from fatigue, literally falling asleep, or just mind wandering, lots of different things. Humans are messy. Some of our other survey work, which we have been able to continue doing during this pandemic when we couldn't put electrodes on people, we've tried to look at a whole host of predictors that we think people vary on, obviously age and gender, their knowledge of these automatic driving systems, their acceptance of automation, a number of these other things. And we're trying to predict where they get their information, what their understanding of it is. And that's kind of ongoing work as well. Finding some interesting things. Obviously, people vary in their tech savviness and things like that. They often, there's often a mismatch between what they think they know and what they actually know about these systems. But some pretty interesting work. And there's lots of individual differences that we've identified in this.
Carol, can I ask you please to come to the end? Oh yeah, thank you.
Yeah, sorry. Okay, so let me just skip this slide. And in conclusion, we need a better understanding of driving automation and the limitations, how that impacts people, new metrics, equipment, and theoretical challenges. How do we measure this? And is it the same for everybody? And I will stop at that. Thanks for your attention.